A lecture on oscillations, Part B. Plots of oscillations, resonance and damp motion. We're looking at here is a mass on a spring oscillating back and forth. If we treat the mass as a particle and track the particle over time, we're seeing a motion diagram. And we see the motion diagram of the particle, the mass over time, plotting out in the form of a sine wave, or sinusoidal motion, going back and forth between the amplitudes. Take that same sine wave, connect the dots or interpolate, rotate it 90 degrees, and plot position versus time in an orientation we're more familiar with. What we see here is we're going from one amplitude to another amplitude. Which one is positive, which one is negative is arbitrary. And it takes one period of time to go from one amplitude to return to that same amplitude. This plots out as a cosine. A sine and a cosine are the same curve. A sine starts out at 0, a cosine starts out at the amplitude. A cosine is shifted, is a shifted sine wave, shifted by a quarter of a period, or a quarter of 2 pi, which is pi over 2. So a cosine is a shifted sine wave by a quarter of a period, or what's known as a phase of pi over 2, a quarter of 2 pi. So the position over time graph would be described here, since it starts out at the amplitude, as a cosine function. We see the position x sub t, the position of the particle, the mass on the spring, over time, xt, is equal to the amplitude times cosine times 2 pi t over the period. Looking at that same type of graph, recognizing that the slope of position versus time tells us about velocity, where the slope is 0, which is at the amplitudes, the velocity is 0, which makes sense. There's no kinetic energy at the amplitudes, it's all potential energy of a spring. The motion is 0 since it's at the maximum displacement. If it's still in motion, it wouldn't be at the amplitudes. And at B and D, the slope is the steepest, which by no coincidence is at the equilibrium, when the kinetic energy is greatest and the potential energy is least. After one period of time, by definition, these simple harmonic motions repeat themselves. So A and E would be identical physical locations, negative amplitude or x minimum on our graph. And after E, the motion will be exactly the same over the next period of time. Hooke's law describes anything that oscillates in simple harmonic motion. The force relates to the spring constant K, the strength, the intrinsic property of the spring, the material and the winding of the material, the strength of the spring, times it by x, where x is the displacement for equilibrium. It could be delta x, or delta L, or L, but essentially it means the displacement from equilibrium, the stretch of a spring or the compression of a spring. The negative in Hooke's law makes it a restoring force, meaning the force is always in a direction opposite the displacement. This is the heart of an oscillation. The force being opposite the direction of displacement means it's always being forced back to equilibrium. This causes periodic motion whenever the net force or acceleration is proportional to the negative of displacement. The object will return or try to return to equilibrium. Hence it will oscillate. Looking at position versus time graph and comparing it to its corresponding acceleration versus time graph, we see they look almost the same. One's a cosine graph. The acceleration graph would be a negative cosine graph, starting at the negative amplitude. We'd say these two graphs are the same but shifted by a certain amount or a phase. Or we can say they're out of phase. So notice the acceleration graph is out of phase with the position graph. But by how much is out of phase? Well, how much does an amplitude differ from the negative amplitude, from a crest to a trough, from a peak to a valley? It differs by half of a period. So the position versus time graph is just like the acceleration versus time graph for simple harmonic motion. except the graphs differ by a phase of half a period, or half of 2 pi, differing by a phase of pi. So we'd say the position versus acceleration versus time graph are differing by a phase of pi, or half a period. Here from the text you see position versus time, velocity versus time, and again acceleration versus time. The dotted lines line up for the same position, velocity, and acceleration for the same periods of time. Notice that each graph is out of phase with respect to the other. Each graph is out of phase by a quarter of a period. From position to velocity is a quarter of a period, or pi over 2. From velocity to acceleration, it's another quarter of a period, or another pi over 2 out of phase between acceleration and velocity. The equations that relate velocity, acceleration, position versus time are shown. And how we can derive those is simply take the derivative of position versus time. The derivative of position with respect to time is velocity. So the derivative of a cosine graph, a cosine function which relates to position, is our velocity graph. The derivative of cosine is negative sine. The derivative of velocity with respect to time is acceleration. So the derivative of negative sine is negative cosine, with the constants of 2 pi f, or omega, pulled out. Our maximum position is an amplitude. The maximum constants in front of the sign for velocity, for the velocity function, is our maximum velocity. And the constants pulled out in the acceleration become our maximum acceleration. So 2 pi f times a for our velocity function becomes 2 pi f is omega. So 2 pi f a, or omega a, is the maximum amount of velocity you can have when sine is 1. The maximum amount of acceleration you can have is when cosine function becomes 1. And that leaves us with 2 pi f, also known as omega, squared times a. Now looking at the v max omega a, or a max equals omega squared a, we can relate this back to the period of a spring, or the frequency of a spring. For a pendulum swinging back and forth, the principles are the same, and the idea of phase still applies. We can think about a phase physically as where the oscillator, whether it's a spring or a pendulum, is during its oscillation, during its cycle, independent of the amplitude or frequency. So meaning when we have it at its maximum displacement, for a pendulum that would be the maximum angle displaced from equilibrium. If we start out at the amplitude, at A, we can say the phase is 0, the phase constant is 0. Since we're starting at the amplitude, we're starting as a cosine function. At B, at equilibrium, if we were to start our observation, or our graph at equilibrium, we'd say the phase is a phase constant of pi over 2. Meaning our cosine function has been shifted by pi over 2 to start at equilibrium. If we start our graph, our oscillation, or our analysis at the other amplitude, the negative amplitude, we'd have a phase constant, or would be shifted in phase by pi. Rather than starting as a cosine at the amplitude, we'd be starting as a negative cosine at the negative amplitude. We'd be phase shifted by half a period from one amplitude, half a period later to the other amplitude, or phase shifted by pi, half of 2 pi. It's another way of describing where the pendulum is in its motion. It's at a phase of 0 or 2 pi at the start. It's at a phase of pi over 2 or 3 pi over 2 at the equilibrium, because cosine of pi over 2 and cosine of 3 pi over 2 is 0. And it's a phase of pi at the other amplitude, or the negative amplitude, because cosine of pi is negative 1. It's just simply telling us where it is physically in its motion. So when the phase is 0, it's at an amplitude. When the phase is 2 pi, it's at an amplitude, so its speed is the slowest. It's 0. When the phase in the cosine function as pi over 2 or 3 pi over 2, it's at its the lowest point. It's when it's moving its fastest, has the greatest speed, the greatest kinetic energy. Note it's often called the equilibrium, the lowest point of a pendulum, but technically it's simply just the lowest point. Simple harmonic motion and circular motion are intimately related. What you're looking at here is an overhead view of a device that shows the relationship between simple harmonic motion and circular motion. It's a ball on a disc. The disc or turntable rotates, bringing the ball with it. If the turntable rotates with a constant angular speed, omega is constant, then the ball will rotate around the disc at a constant angular speed or constant angular velocity, omega is constant. The light from above will shine on the ball, and we'll see the shadow of the ball move back and forth as the ball rotates around in uniform circular motion. The shadow won't be going at a constant speed. The shadow will go back and forth as the ball goes around at a constant speed. The shadow will go back and forth, mimicking the motion of a mass on a spring. The shadow will go back and forth as if it's in simple harmonic motion. So as the ball rotates with constant angular velocity omega, its shadow moves back and forth in simple harmonic motion. We can think about the ball the same thing as a knob on a disc moving around at a constant speed. And from a perspective, the knob seems to go back and forth in simple harmonic motion. This idea is being shown here with the wheel and the piston. If the piston goes back and forth in simple harmonic motion, it'll push on the knob that moves the wheel to move the wheel around with a constant angular velocity. So linear and circular motion are related when a piston causes the wheel to turn. Or if the wheel goes around with a constant omega, constant angular motion, the piston will go back and forth in simple harmonic motion. We can also see this, say, for an object going in a circular orbit. So here, looking at Jupiter, let's pretend one of the moons of Jupiter goes around in a perfectly circular orbit, going around in uniform motion, constant omega, in a circular orbit. So the same motion can be seen when looking at circular motion parallel to the plane it's moving in. So here's a moon going around at a constant speed around Jupiter. But from our perspective, the moon seems to be spending less time as it's coming around Jupiter and going faster, covering more distance as it's going across the face of Jupiter as we see it, and then going slower as it's going back around on the other side of Jupiter. If you look at the dots of the moon's position, the motion diagram of the moon, it looks to be going back and forth in simple harmonic motion, clustering at the endpoints and moving fastest in the middle, like a spring clustering near the amplitudes and moving fast at equilibrium. It's not that the moon is going around in simple harmonic motion. Just from our perspective, from looking at it from the perspective of a plane of the orbit, it seems to be moving the same way a spring would move back and forth in simple harmonic motion. This would be true if you take a ball and a string and whip it around in a circular motion. Looking at the ball and string from the plane of the motion of the ball, from a side view, the ball will appear to be going back and forth in simple harmonic motion. So another way of saying it is, we can say simple harmonic motion is a representation of uniform circular motion from the perspective of a plane where the object is moving in circular motion. This is being shown in your image from the text. We have here an object going around in circular motion. We're attracting the object going around in its uniform circular motion along just one dimension, along the x direction, watching the object go around in its full circle, just plotting where the object is along its x component. As the object goes along in its x component, it traces out simple harmonic motion as we've seen before. If the object starts in the first column at t equals 0 at an angle of pi over 3 along the circle, where the angle of 0 would be directly along the x-axis, and an angle of pi over 3 at t equals 0 as we start analyzing the circular motion of that dot, of that particle, we say it starts out with an angle of pi over 3, or a phase constant. At t equals 0, the phase constant is pi over 3. This is the beginning angle it starts with. That would correspond to a mass on a spring starting out at a phase of pi over 3. And if you calculate cosine of pi over 3, that equals 1/2. So for x equaling a cosine of pi over 3, that equals a times 1/2, or half the amplitude. It's simply halfway along the x-axis. As the object goes around, counterclockwise around the circle, starting at the phase constant of pi over 3, it goes around, and with perspective of the x component of its motion, it moves back and forth starting at half the amplitude, moves back and forth in simple harmonic motion. That's what's being plotted in the graphs in the x versus t and the v versus t graph in the first column. Notice the starting position in the first column is at half the amplitude, and then it proceeds along its sinusoidal curve, a shifted cosine shifted by pi over 3, and then it proceeds along the cosine function, returning to the negative, going down to the negative amplitude and returning back to the positive amplitude and repeating its motion again. If instead the object starts out at t equals 0 at negative pi over 3, it's at the same exact position along the x component, but it's going now towards the x-axis. It's going now towards its maximum displacement in the x direction. So it's going towards the positive amplitude. It's starting out at half amplitude, and as it's rotating counterclockwise, it'll increase its x component of its motion. In a sense, it's going towards the amplitude of its x component, its maximum displacement in the x direction. And then as it goes around in uniform circular motion, it'll be the same as a mass on a spring shown beneath the circle, going from half amplitude to amplitude and returning through its motion. Again, that's shown in its corresponding plot in the middle column, starting out at half the amplitude and then climbing up to the amplitude, and then following the rest of the cosine function. And lastly, in the last column, the object starts out a phase constant of pi, or a half period along the circular motion is when t equals 0. And so it starts out at the negative amplitude and then proceeds. And our x versus t graph for the last column starts out at the negative amplitude, starts out as a negative cosine function, then proceeds along this cosine curve. And the corresponding velocity versus time starts out at a minimum 0, because it's at the negative amplitude, and it goes to the maximum velocity at the equilibrium, and so on. You should redraw these graphs, their position versus time graphs, and the velocity versus time graphs, a couple of times, giving you different various phase constants, and keeping track of how the velocity relates to the position versus time graph, to make sure it makes physical sense. Next topic. As you surely have noticed, springs and pendulums slowly die away. How does the period of motion change, or does it, when a pendulum or spring slowly dies away? The damping of simple harmonic motion due to friction. Looking again at a position versus time graph, we're seeing the period going from one amplitude to the other amplitude and returning to that same amplitude, going back and forth and back and forth. We're seeing the period of this oscillation continue on over time, but the amplitude is being decreased with the same period. Each period of time, the amplitude is less and less. It's the same period of time to go from one amplitude to the lesser amplitude to the lesser amplitude in the same periods of time, so a constant period or constant frequency for this oscillation, but the amplitudes are dying away. This could be a pendulum or spring that's simply reducing its amplitude, in a sense slowing down, but keeping a constant period. This is what a grandfather clock or a pendulum clock would do. It keeps perfect period or perfect time as its amplitude dies away. That's what's being shown in the bottom graph, just keeping track of the dying away of the amplitudes over subsequent periods. How the amplitudes decrease is an exponential behavior. If the amplitude decreases each successive period of time, it's getting less and less that we can describe with an exponential function. So the amplitude decreases as an exponential, and since the potential energy of a spring relates to the displacement of the spring, the delta x or the delta L of a spring relates to the amplitude. So the potential energy of a spring relates to the amplitude. So if the amplitude dies away as an exponential, then therefore the energy dies away exponentially. The time periods for the exponential to die away, well, we'll discuss in the next slide. So the energy dies away exponentially. Energy decreases exponentially. One way to describe an exponential decay is by decreasing by a factor of 1 over the transcendental variable e. 1 over e, 1 over e squared, 1 over e cubed. 1 over e is about 37% or 0.37. So something that dies away exponentially after a time of 1 over e, after a reduction of 1 over e to 37% roughly of the energy, or a reduction of 1 over e squared to 0.13 or 13% of the amplitude or the energy roughly. We call these time periods. We give these time periods the Greek letter tau. This is the amount of time it takes for it to reduce by a factor of an exponential of 1 over e, and then 1 over e again, and then 1 over e again. It's like saying a half-life. How long does it take? A half-life is how long the period of time it is for the energy or the amplitude or what have you to reduce by half. In the next half-life, it reduces again by a half that previous amount. And a third half-life reduces again by that half of that previous amount, a half to a fourth to an eighth, etc. A half-life is a constant amount of time to be reduced by half each time. So in this, what we're seeing here is the constant amount of time to reduce by a factor of an exponential or by a factor of 1 over e each time, or to reduce by roughly 37% each time. So here's our graph, something that's being reduced, but the amplitude is being reduced and the energy is being reduced in an exponential behavior by a constant, in a time constant, tau, of 1 over e each time constant, with the Bezier equation described below from your text that you'll use in your homework problems. You'll explore this idea more so in the upcoming ill. Objects with greater time constants and more damping from friction or drag will die out in shorter time constants, shorter values of tau. The exponential will be more rapid or less rapid if we have smoother surfaces and less friction and less drag. Our last topic is resonance. Resonance is the increase of an amplitude from an oscillation. For example, say you have a kid on a swing, and you repeatedly push the kid on a swing at the right frequency, meaning every time the kid swings towards you, and then as he's swinging away from you, you give him a push. If he swings towards you when you push him, you're slowing him down. If you swing at the wrong time, you may miss. But as he's just moving away from you, you give him a push so he can increase his amplitude. So how frequently you push is you're matching the frequency of when the kid is swinging. You push just as frequently as the kid swings and match that frequency when the kid is near you, swinging away from you, to push him at greater heights or greater amplitudes. So your frequency matches the frequency of the swing, or your period of motion matches the period of your push matches the period of the swing. You're pushing it just right at just the right frequency to make the kid go higher and higher. This is the idea of a resonance, repeatedly pushing a spring or pendulum at the right frequency to increase the amplitude. Now, materials have a natural frequency of vibration. Why? Because materials are made up of atoms and molecules, and atoms and molecules, as we started with, vibrate. Different temperatures, atoms and molecules vibrate more or less, and they vibrate as if they're on springs. The electrical attraction makes them vibrate, and therefore the atoms and molecules have different springs, different bonds, different electrical attractions, depending on what atoms and molecules they are. And so they have a natural springy-like behavior, and therefore they have a natural frequency to their springs. Springs have a particular period, depending on the masses that are vibrating at particular temperatures. So all materials made up of atoms and molecules vibrating. So all materials have natural frequencies of vibration. They may be complicated and they may be mixtures, but they have natural frequencies or many natural frequencies of vibration by their springiness. So you can vibrate objects. If you match them to be the right frequency, you can make objects resonate, such as a rope swing. or a rope bridge. If you make the bridge vibrate at the right frequency, you can get the waves in the bridge to get larger and larger. Musical instruments are made often to vibrate at particular frequencies. So the whole instrument vibrates as a note, or vibrates as chords or combinations of notes to give you a richer sound. A famous example is the vibration along the rim of a glass. If you can get a wave to go along the rim of a glass, get a wave to resonate, so you have a wave trapped along the rim of the glass, the wave can get larger and larger if the wave along the rim of the glass is one of the natural frequencies of vibration of the glass molecules. Their vibration will get larger and larger, just as pushing the kid the right way on the swing will keep making the kid's amplitude increase over and over. If you play the right note on a glass or sing the right note, the glass molecules will start to vibrate. If you keep on singing at that same note, the molecules will vibrate at a greater and greater amplitude until eventually you can shatter the glass. You can ask me to demonstrate this. If you bring in a wine glass, I'll sing at just the right frequency, regardless of the wine glass, to break all the wine glasses. So this idea of increasing the amplitude by resonance is a driven oscillation. Just as you're applying the right frequency for the kid in the swing, it's driving that oscillation to greater and greater amplitudes. So when you match the frequency of the material, you're increasing the amplitude of the material. So the oscillation has a maximal amplitude when the external frequencies, such as you pushing on the swing or the singing, the notes, the frequencies of the notes that are being sung, match the frequency of the material, the swing or the glass or the rope bridge. And this is the idea of resonance. Being plotted here is shown the increase of an amplitude as the frequency is the right external frequency is found, and if it's continued, the amplitude increases and increases. The mathematics is complicated. For your homework problems, you only have to use a few of these and just simply plug and chug.